recent work. I would like to share some recent results about the real-time dynamics of the Chiral phase transition on graphic study. And it's mainly based on this paper done together with my collaborators. This is the outlines of my talk. Firstly, I'll give a brief introduction about the main motivation, and then I will discuss the holographic software model and how it describes the Chiral phase transition. And then I will turn to the real-time dynamics and give a short summary. Okay, let's go to the first part. But we all know that there are two main properties of the QCD vacuum. One is the confinement, which states that no color objects could propagate freely in the long distance in the QCD vacuum. And it's described by the vanishing of the black loop. And the other is related with the main topic of this talk, the spontaneous Chiral symmetry breaking. And we know that the QCD Lagrangian in the Chiral limit is invariant under such kind of transformation. However, this spontaneous breaking symmetry, this symmetry is spontaneous breaking in the vacuum, and it can be read from the mass difference of the current quark mass and the constituent quark mass. And it can also be read from the Chiral partner, the mass difference of the Chiral partners. For example, the rho and the A1, they are transformed to each other under such kind of transformation. And the spontaneous symmetry breaking is described by the nomination Chiral condensate, and it's the main source of the constituent quark mass. This is about the QCD vacuum. If one introduce temperature and density into the system, for example, like in heavy ion collisions, if the temperature of the system is higher than 170 MeV, the colored object could be released, and the system could undergo deconfinement phase transition. Also, the Chiral condensate could be vanishing, and the breaking symmetry could be restored, and the system will undergo Chiral phase transition. And in this talk, I will focus on Chiral phase transition only. It's known that near the transition point, the effective coupling will become large, and the standard perturbative calculation in the textbook becomes invalid. So we need some non-perturbative methods, like the lattice simulations, Danson string equations, and so on. And among them, the holographic method is easier to extend to a finite barrier number density case and non-equilibrium cases. And so I will focus on the holographic study of the Chiral phase transition. Before we go to construct the holographic model, I will briefly recall some physics to construct the holographic model. Firstly, from lattice simulation and the other effective studies, the QCD phase transitions depend on the quark mass of the system. It's summarized in the so-called Columbia plot. In this plot, the horizontal axis represents the UD quark mass, and the vertical axis represents the strange quark mass. And in the upper right corner, when all the three flavors becomes heavy, the lattice works quite well in this corner, and it gives the first order phase transition. However, since the quarks are heavy, the Chiral symmetry is not a good approximation. So it's better to discuss deconfined phase transition in this area. As for the Chiral phase transition, it's better to look into the left part, and the quark mass is smaller. And in the upper left corner, when the UD quark mass is 0, that's the two flavor Chiral limit. And the simulation shows a second order phase transition here. And if you add any finite quark mass, and the phase transition turns to a crossover type, a continuous one. And in the three flavor Chiral limits, when all the quarks are massless, the simulation shows a first order phase transition here. But only when the quark mass is sufficiently large, the phase transition turns to crossover again. So there's a first order region and a crossover region, and in between them, there's a second order line. And by analyzing the critical behavior of the second order line and extract the critical exponents, one can identify the universality classes. And from the results, it shows that the second order lines are divided into two segments. One belongs to the O4 classes and one belongs to Z2 classes. So a successful, consistent holographic model should describe such kind of behavior, at least qualitatively. Besides, since only the hadrons could be observed directly, it will be important to study the inmedium properties of the hadrons and their relations with the phase transition. Actually, in this work, scientists have used the finite temperature perturbation theory, and by analyzing the critical scaling behavior of the operators, they got that the pole mass of the Goldstone bosons, the scaling of the scaling of the pole mass of the Goldstone bosons, the pions, behave like as this form with the temperature, and this T is the temperature, the scale of the temperature, scaling like Tc minus T over Tc. Yeah. And since this critical exponent beta is larger than 0, so we can easily see that the pole mass of the pions should decrease below Tc with the temperature. And this is also observed from the lattice simulation in this work, in this group's work. And they show that from the simulation, they show that the pion mass decreased from its vacuum value to a low value, and this for pole mass. And for screening mass, it goes in a different way, increase. Also, for angel study, for the most of the angel study, they give an increasing pion pole mass below the transition temperature. However, in the earlier study, they show that if one consider the ground condensate, then the pion pole mass will decrease. So perhaps most of the study in angels they neglect the effect of the ground dynamics. Okay, so a successful holographic model should describe such gradients. Okay, so let's go to the second part. There are a lot of successful holographic models. Among them, the software model is convenient to discuss the Chiral phase transition, since it's constructed by promoting the four-dimension global Chiral symmetry to the five-dimension gauge symmetry. Yeah, the Lagrangian here satisfies the gauge symmetry, such kind of gauge symmetry. And this X is a scalar, a metric valued scalar field, and is due to the bilinear operators. The diagonal part actually is just the Chiral condensate. And also, the left-handed and right-handed gauge field is due to the four-dimension conserved currents. So in the software model, it has all the ingredients to discuss the character transition, and I will focus on this model. And in the original software model, they use AdS5 metric and input quadratic form of the digital field in order to describe the linear confinement, the linear behavior of the mass square. So roughly they can describe the experimental data. And later, more extensions of the software model are imposed to describe the other physics, like the form factors, and extend to more flavors by including strange quark, including charm quark. And from their calculation, you can see that the experimental data can be described well. Yeah. So the software model can describe the hadronic physics well. And now we turn to the character transition. And since the original software model cannot describe the Chiral condensate in the Chiral limit, so we need to do some modification. And considering that the positive quadratic form of the digital field is responsible for the linear confinement, and the negative quadratic form is responsible for the Chiral condensate. So we just do a simple interpolation of these two forms. So we introduce this interpolation form of the dilaton. And actually, this is quite similar to Shuyak and Schaeffer's work. And they claim that the different scales of the instanton is responsible for different dynamics, one for Chiral dynamics and for confinement. So this structure is quite similar to that. Yeah. There are two scales. We should introduce two scales. And in order to check the consistency of the software model, we want to check the Columbia plot. So we introduce 3 flavors and 2 light degenerate flavor and 1 heavy flavor, a strange flavor. Yeah. And in this case, we introduce an additional form to the original software model Lagrangian, and this represents the 't Hooft terminal term. And we can derive the equation of motion, and we can solve the condensate for the light flavor and the condensate for the strange quark. And the results is like this. To degenerate quarks, that's when the strange quark mass is infinite. So we only have 2 degenerate light quarks, and we can solve the Chiral condensate. And in the Chiral limit, it's like this red curve. And we can see that at low temperature is finite, and when it turns to high temperature, it turns to 0. And we also check the free energy of this, calculate the free energy, and find that we confirm that this is second order phase transition. And then if we add any finite quark mass, we find that the phase transition turns to a continuous one. So this structure is quite similar to the upper left corner of the Columbia plot. And for the three degenerate quarks, three degenerate flavors, we can see that there's multiple solutions in chiral limit, as this purple line shows. And if we calculate the free energy, we can see that this is the characteristic first order type. It drops suddenly from this point. So in the three flavor chiral limit, it's a first order phase transition. And you also see that if we increase the quark mass, and we find that only when the quark mass reach a sufficient large value, the phase transition turns to a continuous one. So this is also very similar to the lower left part of the Columbia plot. And for 2+1 case, we can also extract the chiral condensate for the left, for the light, and for the strange sector. And from this behavior, we can extract the phase transition order, and finally we reach such kind of behavior. And in this corner is a first order phase transition, and in this area is a first order tap, and in between them it's a second order phase transition. So we can see that this is very similar to the Columbia plot in the left panel. This part is with chiral symmetry could be considered as a good approximation. And we can also extract the critical exponents, and we find that indeed the critical exponents, the second order lines are divided into two segments, and one the critical exponents of these two segments are different. So, and there's a critical point also. So all this structure is the same as the Columbia plot, though only qualitatively. But here there's a drawback. The critical exponents extracted here is actually the mean field results. So this may be because the Lagrange separation and how to correct it, how to do the correction, still under investigation. Okay. We can also add the perturbation to the solution and study the mesons or inmedium properties. Here we only focus on the scalar and the pseudo-scalar sectors because they are most related with the chiral phase transition. After considering this perturbation, and we can derive the equation of motion, and then we can get the spectral function, and from the peak of the spectral function, we can get the mass spectral at finite temperature. The result is like this. We can see that at low temperature, below the second order phase transition point, the pions is always 0, and this guarantee that it's the Goldstone boson of the phase transition. We can also see that the sigma meson, the mass of the sigma meson decrease with the increase of temperature, and then after the transition point, it increases again. Now all this structure is very similar to the calculation from the Dyson-String equation in chiral limit. And later we increase the quark mass, and go to the physical quark mass, which increase the pion mass in the vacuum to the experimental value. And we can see that the qualitative behavior of the sigma meson is not changed much. But now pion is no longer, the mass of pion is no longer 0, but it decreases with the increasing of temperature. So this is consistent with the Sun-Estevano's analysis and lattice results. And also we can check that the pion mass at finite temperature and the decay constant at finite satisfy the GRR relations. It's guaranteed that it's the Goldstone boson. Yeah. So it shows the consistency of the software model again. And also we can see that above the transition temperature, the scalar and the Schroeder scalar emerge together and shows the curve restoration at the hadronic spectrum level. So all these studies show that the software model can give a very well description on the Chiral phase transition and the hadronic physics, their relations. And we can also extend this study to many other cases. For example, to finite isospin density, and we also calculate the pion condensation transition, and we see that the qualitative results is quite similar to the Angelo calculation, and for the left part is quite similar to the lattice simulation. Yeah. So all this shows that the consistency of the software model, and we will tend to study the real-time dynamics of the Chiral phase transition, especially for the Chiral condensate. And one of the main motivations to study the real-time dynamics is the fast thermalization problem in the heavy ion collisions. Roughly in the whole procedure of the heavy ion collisions, it can be divided into 3 stages, and the last 2 can be described by the hydrodynamics and transport models. And from the hydrodynamic simulation, it shows that the first non-equilibrium stage reach local equilibrium at a time around of order 0.1 to 1 Fermi. But this is much faster than from the perturbative estimation. Yeah. Actually, in this stage, one can use the kinetic theory or the Coulomb saturation conjecture to study the physics. However, both of them require the weak coupling conditions. But from the hydrodynamic, the input of the hydrodynamic coefficients, like the shear viscosity over entropy density ratio, the order is at 0.1, which indicating a strong coupled QGP, at least in this stage. So it should be interesting to see what strong coupling method tells us about this stage. Besides the thermalization, at the late time, the early time or the short time, actually the intermediate time behavior is also attracting more interesting. In this group's work, they show that there might be a stage named pre-thermalization, in which the thermodynamic quantities like the pressure or energy density reach their stable value. However, the particle distribution is not. So, but this stage is much, the system reaches this stage much faster than the real thermalization. So they call it pre-thermalization. And this concept has been widely extended in many fields, like in quantum condensed physics and statistical physics. And they have get a lot of more interesting phenomena. For example, in this work, they show that near the critical point, if you choose different initial conditions, then the system evolves with the time. The order parameter evolves with time in different curves. However, if you scaled the time, the system time, and the order parameter with the initial value of the order parameter, then all these curves could emerge together, show some universal scaling. And for the later, the tail, this is related with the thermalization. Actually, this is the critical scaling, critical slowing down. Yeah, since they focus on the critical point, but this phenomena is not observed before, and they suggest that this could be mapped to the pre-thermal state. So it's also, since in software model we can have all these ingredients, so it's also interesting to try to study the real-time dynamics in this time area. Okay, so now let's turn to the real-time dynamics in software model. And since we are consider the evolution of the system inside the black hole background, so it's better to use the Eddington-Finkelstein coordinates. We derive the equation of motion in these coordinates, and we can solve this equation of motion, and we can extract the Chiral condensate as a function of time from the near boundary expansion of this Chi field. But here I have to emphasize that we use the probe limit. So in the formation part, it's like we draw the matter into a heat bath. So it's not a real calculation, not a full calculation. It's just in under a heat bath. And the strategy is that we choose the initial condition from other equilibrium states, and we put it into a finite temperature, a certain temperature, and we try to see how it evolves. And we can choose different initial conditions. And from previous description, it's quite interesting to study the evolution near the critical point. And later we'll see how it happens. Okay. After we extract the evolution, we can see that at temperature below the critical point, the system evolves to its equilibrium value very quick. It's of the exponential decay, and we can see that this tail is very good exponential form, and we can fit the realization time from this slope, and we can see that we can get the realization time evolved with the temperature, and it looks like this. And near the critical point, it diverges, and showing the critical slowing down behavior. And we can directly extract this behavior, and we can still see that this is of the form of 1 over square root tau. And this gives the dynamical critical exponent to say equal 2. Okay. And this results doesn't give more information, but if we if we look into the critical points more carefully, and if we scale the order parameter and the time, the system time with the initial condition, the initial value of the order parameter, and we can see that all the at the late time, all the for the different value they emerge together, and for the early time, we can see that the results will depend on initial conditions. But for the late time, all the curves merge together, and this is related with the thermalization. And we can see that besides this true area, we can see that there's another stage. It looks like the system stays in another steady state. And this structure is actually very similar to that described in previous page. Yeah. So this stage might correspond to the pre-thermal state. Yeah. But to prove this, we still need to do more job, and we'll leave it for the future. Yeah. And also, we can try to extract the dynamical critical scaling. Yeah. We can scale the parameter and the time. We see that all these curves emerge together, and from the scaling behavior, we can extract this x. It should be 1, because in this stage it doesn't change with time. So we can get the initial sleep exponent theta should be 0, and this is again a near field results. However, we can see that the qualitative behavior is quite similar with this with the other model study. We have the critical scale slowing down, and we have another stage. Yeah. The only difference is the exponent is still a mean field. But qualitatively, we have a very similar pattern. Yeah. Okay, let me give a short summary. We have seen that the software model provides a good start point to consider the Chiral phase transition. Yeah. The phase diagram is in good agreement with the Columbia plot. And if we consider the real-time dynamics, we see that it's interesting to see that we can produce a very similar phenomenon like the pre-thermalization phenomenon. And we can extend all these studies in the future.